Hello everyone. In this video, I'm continuing, introduction of differential equations. And the first thing today that I'd like to discuss is the order. Okay, the order of a differential equation. Now, this is basically the highest derivative that you have. Okay, the order. Okay, I guess that word is used for derivatives themselves. Okay, so uh, this is basically the highest derivative that you have in your equation. So I'll write that down. This is basically the highest derivative. This is basically the highest derivative that you have in your equation. All right. So with that said, let's look at some examples. Let's look at some examples. Let me scroll right here. So here I have a few differential equations, as you can see, because all of them have the derivatives of y, the second derivatives, or some higher derivatives of y. So all of them are definitely differential equations. Now, I'd like to classify them, in terms of their order. Okay, I'd like to find their order. So let me make a column right here. Okay, so let me make a column right here. So order, okay, order, and so let's see. I'll just divide it right here. So basically, I want to find their order. Now, the first one, what can we see? Y double prime, okay, y double prime, that basically means the second derivative, right? And this is, 3 plus 3y prime. So this is, the first derivative. Now, this is definitely the highest derivative, right? The second derivative, it's definitely the highest derivative. Okay, so the highest derivative in this equation, it's the second derivative, right? Okay, so the order is 2. The order is 2. It's as simple as that. It's as simple as that. Now, let's move on to the next one. What do we see here? Let me scroll a bit to the left. Okay. So what do we see here? Okay, so e to the y anyways. So you have, we're just going to focus on the derivatives. That's what the order is all about, to be honest. Now, as you can see, the highest derivative is the second derivative. Okay. Now, one thing is, for the order, the powers of any derivative doesn't matter. Okay, no matter you have a square here, this is not the second derivative of y. This is the derivative of y, the first derivative squared. Okay, and what I'm saying is, the powers of any derivative, okay, or any sort of powers, to be honest, don't really matter to determine the order. All that matters is, what derivative are you taking. Okay, so here again we see that the highest derivative is, in fact, the second derivative. So again the order is 2. Again the order is 2. Now let's move on to the next one. So what do you see here? 2 y. Okay, and when you have, suppose, say, when you have y and 5 on top as a superscript, no brackets, this means y to the power 5. But when you have brackets, I think a lot of you have seen this before. This means that this is the fifth derivative of y. Okay, this is not y to the power, whoops, something wrong happened. Okay, this is not y to the power 5. This in fact means the fifth derivative of y. And what we can see here, this is the second derivative. This is the zeroth derivative, or just y, to be honest. Now the fifth derivative is definitely the highest derivative here, so the order is gonna be 5. Okay, let's do one last one. Okay, so again here, I put this example here again just to illustrate the fact that the the powers don't really matter for the order. Again, so what's the highest derivative here? What's the highest derivative here? It's the second derivative, right? This is the first derivative. This is the first derivative. The highest one is definitely the second derivative. Okay. It doesn't matter whether this has a power of 3 or this has a huge power of 9. All of those don't matter. The only thing that matters is the derivative. The highest derivative that we're taking is second derivative. So the order is 2. So the order is 2. So I hope that is enough to illustrate what the order is all about. Now, uh, now what I'd like to do is, okay, take this one equation. Okay, so I'm actually interested in this one, and as we'll see, we'll learn a lot more things. Okay, we'll uh, go step by step and learn a lot more things about differential equations. So let's just consider this equation. Okay, let's just consider this equation. Now, first thing, what's the order here? As we said, it's the order is 2. The second derivative, that's the highest one. So the order is 2. The order is 2. We can say that right off the bat. Okay. Now, let me tell you. Okay, let me tell you that the solution for this equation. Okay, now this differential equation, if you want to classify this fully, it has a really long name. It's a second order homogeneous linear differential equation, and why it has that humongous name, and why the name really exists like that. We'll learn all about that later in even how to solve that. That's not really my purpose here. All that I want to see, okay, so is that I'm telling you that the solution, okay, for now I'm telling you that this is the general solution. This is the general solution for the equation. It is a e to the minus 3x plus b. Okay, I'm telling you that this is the solution. Okay, I'm telling you that this is the solution. Now, again, as I said, we currently don't have the tools to solve this equation, but we can, okay? And given any differential equation and a solution, we can at the very least verify that it is indeed a solution. Okay, we can at the very least verify, and the method is exactly the same as for any algebraic equation. What did we do? When we had some algebraic equation, like suppose say if we go right here, okay. So if you wanted to verify that, suppose say x equals 2, okay, is the solution for this, we just substitute x equals 2 in this equation, right? And what the left hand side would have been equal to the right hand side. That's how we would have known that 2 is indeed a solution of this algebraic equation, right? Same thing here. All that we need to do is find the relevant derivatives, okay, that appear in this equation. Just plug them in and indeed check that the left hand side is equal to the right hand side. So let's try to do that. So if we have y equals a e to the power minus 3x plus b, here what do we have? Okay, so this equation has the first derivative and the second derivative. Let's find them first. Okay, let's find them first. So the first derivative, you just need to differentiate this. So if we differentiate the right side, you get negative 3a e to the minus 3x, right? And the derivative of b, just a constant, is 0. So this is the first derivative. All right, let's try to find, we need to find the second derivative too. We need to find that. Okay, so the second derivative, we just differentiate both sides of this again. Okay, both sides of this again. So what we get from here is, again, you multiply by negative 3, so you get 9a e to the power minus 3x. Okay, so since we have found these two derivatives, that's we have all that we need to plug in here. So let's just do that. Let's plug everything right into this equation. So let's see. The equation is, or at least the left hand side of the equation is, um okay, double prime y double prime plus 3y prime, right? So what is the second derivative? What is the second derivative? That's 9a e to the power minus 3x, right? That's 9a e to the power minus 3x. 9a e to the power minus 3x multiplied by okay, well, that's not part of the derivative. I'll switch color. Plus 3, sorry, not multi, plus 3 uh, multiplied by our first derivative, right, which is negative 3a to the power a e to the power minus 3x. Negative 3a e to the power minus 3x. All right. So wait, too small. So this is basically, 3 into negative 3. This is basically negative 9. So what you have here is actually negative 9. Negative 9a e to the power minus 3x. And it's pretty clear and obvious to see that these two cancel, and what we have at the end is 0, which is in this equation, that is indeed the right hand side, right? That is indeed the right hand side. Okay, so this is equal to my right hand side. So as lo and behold, the left hand side is indeed equal to the right hand side. So we have verified, okay, we have verified that this is indeed at the very least, it's a solution for this equation. Okay, now as I've said, this is in fact the general solution. Okay, so I'd like you to believe me for now. um and this is, why I'm talking about all these is, let's actually try to find a particular solution for this. Okay, let's try to find a particular solution, and for that I'll give you some information. Okay, so the information, okay, the initial condition I'm giving you is the first derivative of y at the at x equals 0. The value of that is 6. Okay, now I want to find, this is the general solution. I want to find the particular solution. All right, so let's use the initial condition. And one thing that's convenient for us, after just to prove, just to verify that that it's a solution, we already found the first derivative. Let's plug these values right into the first derivative. So uh, when x equals 0, the right hand side is, this equation, the right hand side is negative 3a e to the power 0 is just 1. Okay, and the left hand side is, y prime. Okay, and as we said, y prime, when x is equal to 0, that's equal to 6, right? That's equal to 6. So that gives me a is equal to negative 2. All right, but okay, so we got a, but we didn't get b, and we don't have any more information. Yeah, and this is exactly what I was trying to show you is, this is a second order, this is a second order differential equation. And as you can see, you have, in the general solution, you have two constants. You don't have enough initial conditions to solve for both of them. Okay, and in general, you cannot actually, if the order is more than your number of initial conditions, or actually just put that in another way around, if you have a lower number of, okay, if you have fewer initial conditions, okay, then your order, you cannot actually find a particular solution. Okay, so to find a particular solution, you need as many of these extra conditions, subsidiary conditions, initial conditions, whatever you like to say, as many of these conditions as the high as your order is. Okay, or the value of your order. So with that said, let me give you one more piece of information. Let's say that y of 0 is equal to what? Let's say that's equal to what? Okay, now we have two initial conditions, right? Now we have two initial conditions. That's the same number as the order, right? And okay, so that should mean, by what I just said, that we should be able to find a particular solution. Well, let's check that out. Well, we already used this one and found the value of a. Only thing left is to use the other piece of information. Let's try to do that. The other one is, when x equals 0, y is equal to 1. Let's substitute that right here, okay, in this equation. So this is the relevant one. So the right hand side is going to be, so when x equals 0, e to the power 0 is just 1. So the right hand side is going to be a plus b. Okay, but a, as we saw, okay, a is negative 2. So we have negative 2 plus b on the right hand side. On the left hand side, we have y, okay, which is 1. Okay, in this case, this is 1 when x equals 0. All right, and so this gives me a value of b, which is 3. A value of b, which is 3. Now we have solved for both the constants, and that basically gives me my particular solution. That basically tells me that y, okay, the actual solution given my initial conditions and the differential equation is, let's see, um, a is negative 2, a is wait, let's see, a is negative 2, so negative 2 e to the power minus 3x plus, and b is 3. I'll just write it in kind of like in the reverse order, just because it's a bit easier on the eyes. E to the power negative 3x. Voila, this is our particular solution. Okay, the main thing I wanted to tell you is, uh, to find a particular solution, you need as many initial conditions, or subsidiary conditions, as the order, as high as the order is. Okay, suppose, say, if in these examples, okay, obviously some of them are too scary that I probably would never attempt to solve these. But suppose, say, the second one, you'd need two initial conditions, because the order is 2. Okay, Wait, I'll just scroll a bit to the right. Okay. The third one, the order is 5, so you need 5 initial conditions. The last one, the order is 2, and so even if these powers look so scary, okay, power of 3, power of 9, you should still just require 2 initial conditions. Okay, you should still just require 2 initial conditions. Okay, so as I've been saying, number of initial conditions you need is just dependent on the order. All right, with all that said and done, we have a pretty interesting particular solution. Let's actually try to graph this. Okay, let's actually try to graph this. So let me draw a pair of axes right here. Let me draw a pair of axes right here. Let's say this is okay, x. Well, let's say this is x. Let's say this is y. Okay. Now let's just try to think about what this graph would look like. And one thing that helps is we have the y-intercept. We know that when x is equal to 0, y equal to 1. So we have the y-intercept that's going to be equal to 1. So something like this here. And also, we do know that as x approaches infinity, this term right here, e to the minus 3x, it's an inverse reciprocal. This one basically dies down, right? So as x approaches infinity, this basically becomes 0, right? This basically approaches 0, right? So if this whole thing just dies away, what you have left is 3 at the end, right? That's why this graph is gonna exhibit asymptotic behavior. It's gonna approach 3, okay, as x becomes larger and larger, okay, but it's never gonna become 3, okay. So let's actually try to do the graph that. So I'll draw a line right here, although it doesn't look that straight. I'm still trying my best. So this is basically your asymptote. Okay. What I'm saying is, this graph is gonna approach it as it becomes larger and larger, but it's never gonna reach it. Okay. It's never going to become 3. So this is how the graph is going to look. This is how the graph is going to look. Now, why am I going through the trouble of drawing all this? Just to give you a sense of why are we even studying differential equations. Okay, I'm not going to go into that much of depth about applications and all, but you know what happens in the real world is you do some research. Okay, you do some research on some real world problem, and okay, so I'll write that. So you do some real world research, okay, research, and you basically often, instead of just coming up with a function, okay, relating the dependent and independent variables, okay, y and x actually, uh, what you get is information about the derivatives, okay, and you form a differential equation, okay, rather than forming the function explicitly. You get a differential equation on your hands, okay, and this is where all our pain and all our techniques for solving differential equations come in handy, okay. So after we solve it, we get some solution, okay, based on real world data and our mathematical techniques. We get some solution, then we again compare that to a real world situation. So after solving it, the cycle, it's kind of like a cycle. We again recheck, okay, we again check with our real world research whether the solution that we got, does it really adequately describe our situation. Okay, does it really model our situation well. Yeah, the word model is really good here. Okay, so basically we're just trying to make a mathematical model, again recheck it whether it's suitable or not, and this cycle basically goes on. So suppose say this equation, although it looks kind of strange, it's still, I think it's quite beautiful. The thing is, it's actually pretty common in a lot of fields, okay. In particular, since I'm myself studying electronics, this is definitely, you can say that it can be capacitor voltage, okay. Capacitor that is charging, it can definitely be the graph of a capacitor charging voltage, okay. It can also be, if you want a really simplified population model, suppose say like in a culture you have some bacteria, and the food and resources are limited, okay. your maximum population is definitely gonna have, it's definitely gonna be bounded, right? You cannot grow indefinitely if you have a limited amount of food. So this could also be a model. Okay, our differential equation could also be a model for a population. Okay, a very simple kind of population modeling. So that could also be possible. That's the thing. Okay, so often we get a differential equation, especially especially for capacitors. uh, if you study about RC circuits and how we get these solutions, it all starts from the differential equation and then we work towards the solution. Okay, so that's really the beauty or the essentialness of differential equations. Anyways, that's enough blabbering about uh, all that. Let me just cover a few more things. Last two things I need to cover. Mainly one is, and it's not something that you encounter a lot, especially in a beginner calculus, differential equations course. You have another thing. Okay, besides order, you have another term which is degree. Okay, which is degree. So I'll write that down. Degree. Okay, and this is not the same as order, although in an algebra order and degree they're interchangeable. Here they are not. Degree is actually, let me write that down. it's the power it's the power, okay, of the power of, or the index or exponent, whatever you want to call it, of the highest. Okay, so I'll write that in caps. Of the highest, of the highest derivative, of the highest derivative. I'll just write der. So the important thing here is to realize, okay, first thing, it's the power of the highest derivative. It's not the it's not the value of the highest derivative itself. Okay, and the thing is, this other point, okay, of the highest derivative. No matter what, you need to choose the power of the highest derivative. So first find your highest derivative, then just then just pick out the power. That's all that you need to do. So let's actually here, with the same examples, let's try to find the orders. Okay, let's try. So not orders, the degrees. The degrees. I really shouldn't mix them. Okay, let's try to find the degrees. Okay, of these differential equations that we just saw a while ago. So here, what do we have? The first one, let's see. Again, the rule is, first find your highest derivative. So that's this one. Okay, the highest derivative term is this one. Now, what's the power of this of your highest derivative? Well, there's nothing explicitly said here. So definitely, just like in algebra, your power is one, right? Your power is one. Okay, so our degree is actually one. Okay, our order is two. Okay, but our degree is one. All right. Next one. Let's see. Here, your highest derivative is your second derivative, right? And again, the power of that is one, right? I might say, okay, so but the derivative of y, dy by dx, it has a higher power. Right? It has a power of two, which is definitely more than this. But again, that does not matter. As I've said, that does not matter. What matters is, first you choose your highest derivative, and then the power of that is just going to be your degree. Okay, so even if other derivatives have a higher power, they don't count. Okay, so my degree here is again one. My degree here is again one. Let's move on to the next one. So here, it's fifth derivative. It's a fifth derivative. That's the highest derivative. And again, the power of that, okay, power of that, it might look a bit strange to write it like this, but the power of that, okay, the power of this is one, right? The power of this is one. Okay, so my degree again is gonna be one. I might have wanted to redesign these problems a bit before doing this, but anyways, the fourth one should be a good example, definitely. Here, what do you have? The highest derivative is the second derivative. Okay, so and what's the power of that? 3. Now the degree is definitely going to be 3, even if you have a very humongous power here. It doesn't matter, because this is not the highest derivative. Okay, so your degree is going to be 3. Your degree is going to be 3. All right. Now, as I was saying before, okay, what I just skirted past just a while ago. Why don't we talk about degree a lot? Especially the maximum I think you see in a beginner's calculus course is just some discussion about the degree and stuff like this, just how to find the degree. But after that, the degree you'd almost not see that being talked about ever again. So why is that? And it's because higher degree differential equations are a real pain. They're really difficult to work with. So in a beginner's differential equations course, you're definitely not gonna talk much about the degree, because all your equations or the ones that you are gonna deal with are gonna be first degree equations, are gonna be first degree equations. That's why this, you could even say, if you wanna put it that way, it's not really that important of a factor, okay, as the order, at least for us. Okay, so with that all said and done, that's basically all that I wanted to discuss. The main things. Just one last thing I'd like to discuss. It's just some terminology. It's not really that important again to make a fuss about it. The thing is, see these conditions. Okay, they are they're given at the same value of y, right? Sorry, not y. They're given at the same value of x equals 0, right? And so technically, if these conditions are given at the same value of x, only then do you actually formally call them initial conditions. Okay, so suppose say I told you that y of 0 is equal to 5 y prime of pi. Okay, even at x equals pi, let's say that's equal to e. Okay, so anyways, I just made them up. The thing is, these conditions, they're definitely not given at the same value of x, right? They're not given at the same value of x. So here x equals 0, x equals pi, they're not the same. These are actually called, just because the values of x are not the same for these conditions, they're called boundary conditions. They're called boundary conditions. It's just a different naming. Again, as I've said, there's no real need to make a lot of fuss about this, or fret about this. These Whether you have boundary conditions or initial conditions, these are just some extra info, just so that we can find our particular solution. That's all that they are. So with that done, that's the end of this video. So I'll see you in the next one, where we'll start actually solving differential equations, learning the methods to solve them. So yeah, goodbye and study smart.